This presentation covers file signatures and data carving. This is for classes at University of Central Florida. My name is Rick Lineker. So here's an overview of what you're going to learn in this series of presentations. We're going to talk about file formats, sort of what is a file format and what distinguishes them from each other. Data types, and you might be familiar with some of these, such as text, binary, imaging, so forth, and signatures. And actually, signatures turns out to probably be one of the most important things you learn in this section. So we're going to start off with images. And images really come in two major flavors. The first is a vector image. And a vector image is simply a lot of commands with which the renderer can draw the image. So really, essentially, it's a list of draw commands. Bitmapped, or often called raster, this is a series of RGB triples. For instance, I'll have one triple for one pixel, another triple for another pixel, and so forth. And we'll go a little bit more into detail about this in just a minute. This could be ARGB quads. And ARGB is the same as RGB, except in ARGB, the A stands for the alpha channel. So in some images, there's an alpha channel. So for right now, I'm going to gloss over the notion of an alpha channel. And the reason I'm going to do that is not to leave you in the dark or not teach you something that maybe you need to know down the road. But I just want to make sure that we all fully understand RGB, and maybe at a later date. And maybe at a later date we can add the A to the ARGB. So vector images. The most common types you'll see are PostScript, possibly EPS. Now Photoshop has kind of its own file format. It's proprietary and not technically a vector format. However, it does have a lot of vector components to it. So let's go ahead and take a look at an EPS file. And here's the one I'm going to go ahead and use and look at. And I just want to point out that it's nothing more than a text file. So I'm going to drag it over to a notepad shortcut, which is out of your view. And here we go. Okay, and you'll notice that this is all readable. It all looks like text because it is. This happens to be the palette. The palette is all the colors that are used in the image. Now, as you can see, this almost looks like C code or Python code or something like that. It's just a series of commands that tell the renderer how to draw this thing. So as you can see here, EPS, and the same for PostScript, is true. It's just a series of commands. So bitmap or raster images are completely different than vector images. Vector images, as I said, was a list of drawing commands. But bitmaps are a series of pixel specifications. And as you can see in this image here, it's really nothing more than, and this is blown up, but they're dots on the screen from left to right, the next line left to right, the next line left to right. And that's really how they order. They start on the top line and they go left to right, next line left to right, next line left to right. And if you take a look at this image, you can see that there are discrete units. Although they look like small squares in this image, they would be small squares, probably smaller than you can actually see with the naked eye in real life. This just happens to be magnified. So each pixel is composed of 3 channels: a red channel, a green channel, and a blue channel. And that's where we get RGB. I've been using RGB before this without really defining it, but it stands for red, green, and blue. So at the core, a pixel has 3 color channels: red, green, and blue. And by combining these, a visual color is derived. So I know I've had friends ask me, well, those aren't the primary colors, but this is the way it works in electronics and computers. But we're going to take a look at a mixing demo in just a minute. Okay, this online demo gives us a really good idea of how you can mix red, green, and blue to create their derived colors. So let's just start with a single color. If we take red and we bump this up, we start getting a really dark red. We actually have to bump it all the way up to its full value to get a full bright red. And notice that each of these color channels is a byte, and a byte has an unsigned value ranging from 0 to 255. And as you notice down here, you can see that when it's at maximum value, it's at 255. When it's at minimum value, it has 0. Please note there are no negative values for palettes. Although if you're a programmer, you know that chars or characters have negative values. But bytes, such as those in Java or bytes in C# or unsigned chars in C, don't have negative values. It's the same thing here. We don't have negative color values. So let's go ahead and bring blue all the way up. And you'll notice you get a nice bright blue. And now let's start mixing. Let's go ahead and take red and blue, and we should get some sort of purple. And this actually is called magenta. It's a type of purple. To get a real true purple, you'd have to move both of these down a bit, because purple's a bit darker than that. And now if we put a little green in there, you can see this very center spot is where all three come together and mix. Okay? So I might suggest that I'm going to go ahead and paste this into the PowerPoint slides in just a minute so you have the link. But this is a really good demo to see how the colors mix together. So here I copied in the link to the mixing demo. It's actually a really long link. So let me give you about 15 to 30 seconds to go ahead and take a look at that, copy it down if you want to. Okay. So back to RGB pixels. A pixel, of course, is one of those squares or one of the dots on the screen. RGB pixels normally have 3 bytes, right? The bytes each go from 0 to 255, and each of these contains one of the color channels, red, green, or blue. Now in video memory, the data is a continuous sequence of RGB triples. I know I've been talking about scan line, left to right, scan line, left to right, scan line. There's no notion really of scan line. It's all just one contiguous memory buffer. So now I'm going to do a demo, hopefully, and explain further how the pixels and the data actually work together. Okay, so I'm using Microsoft Paint, a combination of Microsoft Paint and Notepad to do this illustrative example. So the first thing you need to know is that Paint is super zoomed in, so you're going to see actually large blocks for each pixel. So let's go ahead and draw a pixel here. There's a pixel drawn. Now what's going to happen is your data is going to look like this, 0, 0, 0. Because black is 3 values of 0. The red is 0, there's no red. The green is 0, there's no green. And the blue is 0, there's no blue. But let's say we want to go over here and we want to grab red and draw a red pixel there. Okay, now red is full red, 255 is full, remember. There's no green and there's no blue. So far, that's what our data in memory looks like. Now, we're going to go over and grab a blue pixel and paint that in. And give these a little space so you can see the difference in the pixels. So blue has no red, no green, and full blue. Okay, green, oops, green. Green will have no red, full green, and no blue. And let's go ahead and do like a purple. Let's pretend it's magenta. Here we go. That'll be good enough. So this is going to combine red and blue. So red, I'm guessing right now, 200, no green, and 200 blue. We can actually see with paint what the actual color is if we go to edit colors, and that is actually 163, 73, 164. 163, 74. Is it 164? I don't know. This is what happens when you're making a recording. Anyway, so you can see how the memory is building up, and it looks like just your normal data buffer. However, you can see up here that there's a really nice display of pixels. So let's move on to the idea that raster images can actually be indexed. Many times we think of image data as being just simply RGB triples, and these consist obviously of 3 bytes, one for each of the color channels, red, green, and blue. But sometimes images are indexed, and what this means is that these types of images will have a color palette table which acts as a dictionary of all colors that the image is using. That means all you need is a single number and you get an index into the RGB triple. And the idea is that this will save you space as you save the image to disk. So let's take a look at the following palette. Now this palette has 24 colors, and they represent a fairly reasonable distribution of colors. And I've got the hex value, the decimal value, and the red, green, and blue channels, and you can see on the right side you can actually see the colors. Now let's say I want to store black. Well, if I wanted to store black as an RGB triple, I'd store 0, 0, 0. But in this case, if I wanted to just store it based on this 24 value table, I could just store a single 0, and 0 would represent the 0 index. So let's say I wanted to store index 10 right here. That would correspond to this dark magenta color over here, and that would be a savings, quite a savings, because normally I would have to store 255, which is FF, 00, and 88, 3 bytes for that color, but instead I can just store this one single byte of 10. So it's a big savings in terms of what you store. So some thoughts on indexed images. The first thing you need to know is that JIFF images are always indexed. The second thing you need to know is PNG images are only sometimes indexed, and it really is going to depend on how many colors are in the palette table. If a PNG image is more photographic and has a wide spectrum of colors, using a palette is not going to save you any storage space. So it just won't save it as an indexed image. BMP and JPG images are never indexed. Those file formats actually don't have an indexing mechanism. We're going to go through now and talk about the 4 most common image types. Those are going to be BMP, GIF or JIFF, of course nowadays they say GIF, PNG, and JPG actually. So let's start off talking about BMP files. So the file extensions are always BMP. Now bear in mind, anybody can change the extension of a file, and it's a fairly common way to sort of obfuscate what a file is. So you can't necessarily take a file extension at face value when you're doing an investigation. So we're going to talk about how you find the signature of a file and can verify what type of file it is. It's completely uncompressed. Now, in all fairness, there is a compression scheme that is built into the spec, but nobody ever uses it. So I always say it's completely uncompressed, although there is the remote possibility somebody could use the built-in compression. The pixel format is simply RGB triples, as we've already discussed. These also could be ARGB quads. So, but for right now, as I said before, we're going to gloss over ARGB and just stick with RGB for right now. There's one really interesting thing you need to note about BMP files, is each scan line has to be a multiple of 4 bytes. So if for whatever reason the system gets to the end and there's maybe an odd number of bytes or not a multiple of 4, it will actually pad that. So there's a potential that for BMP files you could get small pieces of unused or unnecessary data at the end. Their only purpose though is to go ahead and pad it so that it's an even multiple of 4. So there's a signature of BM standing for bitmap at bytes 0 and 1 of the file. Now there's a really low-tech way of finding out if this is actually starts with BM, and I'm going to drag this over to Notepad, which will actually load it up, even though Notepad normally only loads up text files, but you can still drag a BMP there and you'll see. And this is going to take a minute because it's a pretty big file. Let me drag that over. Okay. You see how the first two characters start with B, M? Okay. So that just shows you at least that part of it checks out. So the reason that you can't count on BM is because other files might actually start with BM. There's no, BMP files don't have a lock on starting with BM. For instance, you might easily have a text file that starts with BM. So when this is the case, you're going to have to look for other ways to make sure that it's a BMP file. So right after that, these are the fields that are the first part of a BMP file. The first field you can see is the type, which is BM. And then after that, the size, reserve 1, reserve 2, and offset bits. But I normally am not going to use those to figure out, to try to determine if this is a valid BMP file. Normally I'll use the width and height and planes and bit count. Those four together will give you an idea if it's actually a valid BMP file, or at least it will give you a good guess. Many of these other fields are really not going to help you, such as compression, BI size, image, pixels per meter, and stuff like that. So I use those four fields and to at least give me a good guess if it's a valid BMP file. So there's a file utility that is a commercial program, but there is an eval version that you can use. It's called WinHex, and this is what we're going to be using. So we're going to use this a lot in this course for looking for file signatures and doing data carving. So just go to x-ways.net/WinHex and you can download it. Okay, so let's go ahead and take a look at our file, our BMP file that we looked at. Let's look at it within WinHex. You see two representations of the data. Here you see a hex representation of all the data. Over here on the right side you see the actual more human readable. Starts with BM. Now the width, the image width actually starts at byte 18. That's 18 decimal, which actually is 12 hex. So you see BC 020000, and that does not look to me like a number that I'm going to be able to use. But there's something in IBM code that you need to realize. Everything is a swapped byte. Okay, so let's say you have a short or a word which is made of 2 bytes. In order to, when you're reading it, to actually look at it and be able to calculate what it is, you swap the bytes. If it's 4 bytes or a double, 4 bytes or a D word, first you swap the 2 words, and then within each word you swap the bytes. So in order to figure out what BC 020000 is in decimal values, I'll go up to WinHex Tools and it'll load up the calculator. And so we're going to ignore 0000 since it doesn't have any bearing on this. But what we're going to do is we're going to say hex, we're going to say 2 BC. Notice I swapped them. 2 BC is BC02 swapped. And under the decimal equivalent, you see that it's got a value of 700. So 700 is actually a reasonable width for a BMP file. Okay, and then we could do that for the height. The height, let's see, 12, 13, 14, 15. The height is going to be 1A4. So let's go ahead and do this. Clear this out. 1A4. So it's got a height of 420. Still a reasonable value. So this is how you can actually go through and use WinHex to determine if your values are all reasonable. Now, there's another way to do this, and I find it easier than using WinHex. But a lot of you are not going to want to do this. This course does not require programming. However, what you see in front of you is a program, and I'm only going to touch on these so that those of you who are like-minded and want to write programs can do so, and those of you who don't want to write programs can just get a better understanding of what we're talking about by looking at what I'm doing here. So here I'm going to open up that mountain.bmp file. And notice that there are two data structures. One is called bitmap file header and one is called bitmap info header. And when I talked to you in the PowerPoint slides, I didn't separate it into two sections. But truth be told, the first section is all about the file, and the second section is all about the actual image information, things such as width and height and so forth. So let me go ahead and set a breakpoint. So now we're going to talk about the JIFF file format. And you might sort of question how I'm saying that word. The originators created the file format in the mid 80s, and they said it was pronounced JIFF, just like the peanut butter. However, over the years, it's morphed into GIF, which most people say nowadays. But since I've been around for so long, I'm going to continue to say JIFF as the original inventors said. So the file extension is .gif, and don't forget we've talked about the fact that anybody can change a file extension. You could change .gif to .exe, .docx, anything in order to throw you off as an examiner. Okay. Now, interestingly enough, what we just talked about, BMP, is not compressed, although I did mention that there is a compress option which is never used. But JIFF data, not the palette, not the format, excuse me, not the header, but the actual image data is compressed with LZW. And LZW stands for Lempel, Ziv, Welch. Lempel and Ziv were two academics who created the original LZ77 standard, and then Terry Welch, who worked at Unisys, eventually added something to it to get about another 10 or 15% compression. So Lempel, Ziv, Welch. Now, here's a little bit of interesting history, is that Unisys, Terry Welch worked at Unisys, so he couldn't make any kind of claim, copyright claim over LZW. And since he worked at Unisys, they actually were able to patent LZW. So the JIFF compression was actually patented by Unisys. And at a certain point, Unisys got really litigious about it, and JIFF was a freely used and distributed file format. But at a certain point, Unisys got really sticky about it, and they required that any developer who wrote JIFF files would have to buy a license from Unisys. Now, to read JIFF files, such as browsers and so forth, it was fine. They didn't have any problem with that. But if, let's say, I wrote a paint program, which I've written several paint programs, and I wrote a paint program maybe that saved files as JIFF, then I would have to pay a licensing fee in order to do that. The patent has since expired, and so now you don't need to pay that license. But it was just interesting that for many years you had to actually pay this licensing fee. And sometimes I wonder if that's why the JIFF file format did not sort of progress and evolve and so forth. I'm wondering if that was the reason that it was overshadowed by formats such as PNG and JPG. And we'll talk about both those formats in a minute and the advantages they bring. Another thing I need to point out is that JIFF uses an indexed pixel format. So JIFF starts with a palette at the very beginning. The palette has all of the defined colors, and there are three values, red, green, and blue. And then all it does is to store those values. Instead of storing the actual RGB values, which would be 3 bytes, it stores a single index into those bytes. So you're already getting the 3-to-1 compression ratio. Now, JIFF, since it never really did evolve, is sort of stuck at 256 simultaneous colors. So the number of colors is limited, and that's why you can easily get away with the 3-to-1 ratio. The file format has a signature JIFF89A. Those are the first 6 bytes of the file, bytes 0 through 5. You may actually see some older files which say JIFF87, and I have not seen any of these for 20, 30 years. So 20 years, I guess. Anyway, but there is a potential that you would see a file signature of GIF87. So other files might actually start with JIFF 89A. You may have, say, a text file that starts with JIFF 89A. So I might have this, JIFF 89A is the start of a JIFF file. And this is a text file, certainly, but if I was looking only at the header, then I might think it was a JIFF file with a .txt extension. So just be really careful that just because we have the header doesn't mean it's necessarily a JIFF file. So you need more than JIFF 89A as the header to identify it specifically as a JIFF file. Now I'm going to go through and talk about the data, the header data that's part of the JIFF file. And we have to, besides the header signature, JIFF 89A, we have to look at sane values for all of these things. So obviously the first 6 bytes are JIFF 89A. Then there are 2 shorts that come, canvas width and canvas height. Now let me start by saying shorts, in today's image formats, we're never going to have shorts, we'll have full ints or full longs, because shorts only go up to 65, 535. And by today's standards, we would view those as really small. But the point is that canvas width and height are essentially ignored. There's sort of no notion in today's world of a canvas width and height. Now, when I've written actually JIFF compressors, I save the width and height of the canvas the same as the width and height of the actual image. But what would happen is before, you could have a large canvas with a smaller JIFF image. And so this was just a way of saying, okay, what's my larger canvas? And later on we'll have a left and a top where we could say, well, where's the JIFF image positioned within that canvas? But essentially you can ignore these two. The logical screen descriptor is actually, it's a single byte. However, it's got a lot of bit fields that actually describe what's in the image. Background color image. Now JIFF was really probably the first image format to have a background color. Okay, there's a global color table that comes. There are 256 RGB values. Now, very important to note, 256 RGB values, but to find out how many values that is in real life, you got to multiply by 3 because you got red, a single byte, green, a single byte, and blue, a single byte. So you have to say 256 times 3, and that should be 768 bytes. So shortly we're going to do some data carving where we pull out the palette out of a JIFF file. So just remember that fact. Okay. Then there's an image separator. The image separator has a value of 2C hex. It's the same as a comma, ASCII comma. And that basically separates the previous data with an actual image. Now, in all fairness, JIFF images themselves can have multiple images within them. And that's how you get the JIFF animation, which we're not going to be going into right now. But JIFF files can have multiple frames within them, and they're all separated by this image separator character, which is 2C. Next comes left and top. And remember what I said about the canvas. Left and top tells you where inside of there that the image is going to be placed. I always ignore these, and when I go ahead and write a compressor, I just make them 0, 0. So for those 2 shorts. But the things that we're really going to focus on are width and height. If we are able to determine that the width and height are sane values, not negative values or not some sort of a really weird, maybe a width of, say, 8,000 and a height of 2, which I guess is possible, but that's going to sort of clue you in that you may be on the wrong track. So this header data is really important for your investigation. Okay, so here I have a JIFF file opened up in WinHex, and you're going to notice the first 6 bytes are JIFF 89A. So I've got 2 things going for me already. It was a .gif extension for the file, so that's really good. And the first 6 bytes are JIFF 89A. Okay, so already I'm off to a pretty good start. So we can take a look after the first 6 bytes, and we see the screen width and the screen height. And if you want, you can run a calculator on that. Let's see, 488 for the height would be, let me write there's a calculator option here under Tools. So 488 hex. 488 hex is going to be a decimal value of 1160. So you can always go through and calculate that. So you got width and height of the canvas, but as we said, the canvas is largely going to be ignored. The palette data starts at byte 13, okay, because the first initial area here is that header, but the palette starts at byte 13. So I'm going to use WinHex now, and I'm going to mark that as the beginning of the block. Now if I go 256 times 3 characters down, I should get to the end of the palette, which is right here. See, and C2C, that's the separator. So if I go 768 characters, which is 256 times 3, I get to there, and then the following byte is the separator. Now, the next thing we're going to do is called data carving. I've got these blocked off, and if I right-click and say Edit, Copy Block, normally, let's say into New File. Okay, I'm going to save this as my palette, and I'll just say DAT, so it's because it's going to be binary data. Okay, so now I have that isolated on its own as the palette. It's also saved to disk. So that's your first example of using WinHex to do data carving. But now let's go back to the JIFF file. Once I'm done with the palette, there's 2C. Okay, that's the separator. Then left is 0, 0, value 0. Top is 0, 0, value 0. And then width and height, 480 and 288. Notice that those are the same as the canvas width and canvas height. As I said, when I wrote compressors, I always save the canvas width and height the same as the image width and height. So let's see, you can easily calculate 480 and 288 with a calculator. I'm going to do that. So 480 hex, 480, that's a decimal width of 1152. 288 is a decimal height of 648. So that's how you can go through and manually figure all of this stuff out. Now I wrote a C++, really a C program because I didn't use any C++ features, but I wrote a program that would read the JIFF header, the palette, and then the image data, or the frame data really. So here's the initial header data structure. Notice that it's followed by the global palette. And here's the actual image or frame, really should say frame descriptor, that's okay. Okay, so I go ahead, open the file, read the header. Now this is going to go through, there's a small amount of data in between that it needs to skip over. Finally it reads the actual frame data. And if we hover over the data structure, we will see image left and image top 0, as we've already talked about. Image width 1152, same as the screen width. Image height 648, same as the screen height. So these are same values, and they give us a very good indicator, along with the file extension being JIFF and the first 6 bytes being the correct signature. This gives us a really good idea that this is truly a bona fide JIFF file. Okay, so now on to the PNG, or Portable Network Graphics file type. Its extension is PNG. There is sort of a new version of PNG that does animations similar to the old JIFF animations, but we're not going to cover that in this course. So the compression for this is compressed with deflate. Deflate is actually based on the old LZ77 standard that was created by Lempel and Ziv, and unlike LZW, it never had any kind of patent issues, so it's freely usable. That's why Zip itself doesn't have any kind of licensing fees or anything else that uses deflate. Deflate is sometimes called GZIP. The pixel format, there are two options for PNG for the pixel format. In today's technology, indexed is rarely used. So an indexed PNG would be used only if you don't have very many colors. Because once you pass 256 colors, or especially once you pass, 65,000 colors, PNG becomes better as RGB rather than indexed, okay? Because the actual palette adds a lot of size to the file, and so at a certain point there's a break-even point, and you just might as well go to RGB without it being indexed. So whether it's indexed or RGB depends on how many simultaneous colors there are in the image. The file signature starts with an 89, and there's kind of an interesting story about this. This was put there so that you could easily tell if whatever program was accessing this would be able to support 8-bit values, okay? Because hex value of 89 has the high bit set, which if you're using a lot of old DOS commands wouldn't work because that high bit is set. And then after that single byte comes PNG. So the first 4 bytes of the file, bytes 0 through 3, are this hex 89 plus PNG. So other files might start with 89 plus PNG. You might even have a text file that starts with that. Now, modern day text files have no problem with the high bit being set, so that's not going to be an issue. So you need more than 89 plus PNG to really verify that it's a PNG file. So here's what you get with a PNG file. You get the signature, obviously, that's 4 bytes. And then these next things are really still throwbacks to making sure that DOS handles this correctly. There's a carriage return line feed, that's a 1310 value. There's something called stop display, which has a value of 1A hex. Now the reason this is there is because if someone actually used the DOS command type and they said type like filename.png, then actually when it hit the stop display, it would stop showing. Okay, the type command would actually bail out. Finally, there's a line feed. Now, after that initial header, ping is nothing more than a bunch of chunks. Chunk, 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 chunk. Everything is dealt with in terms of a chunk. But required is the first chunk of IHDR chunk. And IHDR actually determines sort of the width and height of the file and sort of a lot of the things about the entire image. So it's always required that the first chunk is the IHDR chunk. Now, chunks are always in the same format. You have a length, 4-byte length, you have a 4-byte type, then you have your data, and followed by that, the data is a CRC. This chunk happens to have the same length, the same type, and the type will be IHDR, and then it's going to have the data for the IHDR, which is width, height, bit depth, color type, compression method, filter method, interlace method. And then following that would be the CRC for this particular chunk. Now we're only going to take a look at width and height because that's really all we're concerned with, because remember, we want to try to see if this image has a sane width and height. Okay, so here I have a PNG file opened up in WinHex. And as you can see, we have 89 hex as the first byte. Then we have, this doesn't necessarily look like PNG, but if you look over here, you'll get PNG. Okay, so there's your signature. And then there is that carriage return line feed, which is a 1310 pair. You have the stop display 1A, remember, followed by line feed. So these first 8 bytes mark the initial PNG header. Next comes a chunk. So we have 4 bytes of chunk length. 13 is what it turns out to be. So this chunk is going to have a length of 13. And then we have the chunk type, which you can't tell what it is there, but if you look over here, you can see the chunk type is IHDR. Okay, and one thing I do want to point out here early on is that PNG is portable. So it has to work on Mac, Sun OS, Linux, PC, whatever. So remember how in BMP we had the reverse bytes and the reverse words? We don't have that in PNG. It's sort of in a straightforward, sort of normal type of a setup. So here we go in order of least most significant byte through most significant byte. And so you don't have to do that byte swapping to evaluate the values. Okay, after IHDR, then you get your actual width, and image height. So the image width is 480 and the image height is 288. And I know we already did this, but let's do it again just for completeness. 480, that's 1152 decimal. 288, that's 648 decimal. Okay? Those are same values, so we have the right file extension, we have the correct signature, and we have same widths and heights. So we're off to a good start. Okay, so here I've written a program to open up a PNG file and look for the appropriate data. So my first data structure has this test byte, room for PNG, carriage return line feed, the stop display, and then that final line feed. Okay, this is the first 8 bytes of the file. After that comes the chunk length, the chunk type, and then the image width and height. Of course, this other stuff we've talked about, but for right now, I'm not going to be looking at those. Okay, so what does this program actually do? This program opens the file. Right here, it opens the file. It reads in the initial header. It reads in the initial chunk. Now, what in the heck is this? Why am I going to swap? In my explanation, I said, well, we don't need to swap. That is correct for some CPU architectures. But remember, PNG is portable, and it's not byte and word swapped. However, I am now on a PC, a Windows-based PC, and in order for me to make sense of this, I have to actually re-swap it so that it is swapped. So up here, I wrote a swap function, not the most eloquent swap function, I just did it very quickly. So it reorders those bytes so that in the PC world, I'm going to have the correct values. So we go ahead and set a breakpoint there. Okay, run this. Okay, so it's going to open the file, and now these the initial header should be, okay, I've got 89, then PNG, followed by carriage return line feed, the 1A stop display, followed by that line feed. Now here's the important part so we can determine if the width and height are actually correct. Well, here the type says IHDR, so we know that we're right on there. Then width and height, 1152 by 648. So this shows us that we have same values, and we have 3 of 3. The right extension, the right signature, and same width and height values. So we'll probably have a legitimate PNG file. So the last image file format I'm going to cover is JPEG. JPEG is also known as Joint Photographic Experts Group. Its file extension is JPG, or sometimes, very rarely, you'll see JPEG. That actually happened a lot more in the early days than now. I'm not sure you're going to see it very much at all. So the compression for JPEG is very, very interesting. It's actually a 2-pass compression. The first pass is a lossy compression, where the data is analyzed and some amount of data integrity is lost. And that's why JPEG doesn't work for very square or very sharp images, but it works for more photographic images, because in photographic images you don't have to worry about retaining the sharpness, whereas if you have like line drawings and stuff, you'll really lose the sharpness. So the lossy phase goes through and you actually do lose some data integrity, but if it's done correctly, say for a photograph, you won't even notice it. And after the lossy phase, then there's a lossless phase, which uses Huffman compression, which is dates back to 1952, but it's still very effective for JPEG. The pixel format is always going to be RGB, and these are going to be RGB byte triples. The signature is JFIF, but it's not, the file doesn't start with JFIF. It actually starts with some markers that can be found at the beginning of the file. So let's see, you'll have markers, and the markers actually normally are going to be 4, but you can have any number of markers, and the markers are always followed by 00, hex. That way you know how many markers you've got when you're at the end of the markers. Finally, the signature, JFIF. Then you have header data, and then width and height. Okay, so here you can see a JPEG image opened up within WinHex. Now notice over here, I said that the signature was JFIF, and that's correct. But also notice that it does not start at the very beginning of the file. So you look over here in the hex dump, and you see values, and these are all markers. But then they end with 0010. 0010 indicates that you're at the end of your markers. Okay, and then comes JFIF. So far we've got 2 out of 3. We have the correct JPG extension and we have the correct JPG signature. Okay, now let's go to the width and height. 1A4, 2BC, those are the width and height. 1A4 is a decimal of 420. 2BC is a decimal value of 700. So you have a width of 700 and a height of 420. So those are sane width and height values. Sometimes you will encounter images that are concatenated. So let me go ahead and concatenate 2 images and let's talk about the ramifications. So let's see, dir/.png. I think I just have a single PNG file in this folder. Okay, so let me go ahead and create a copy of that. Copy untitled.png, sample.png. Okay. Now let me mash them together, concatenate them. So I'll say copy/b untitled.png plus sample.png to combined.png. Okay. So dir.png. And you'll notice that combined.png is actually larger than the other two, twice as large, as you would expect. Okay, so let's take a look and see if we can find combined.png. There it is. And if I just double click it, if I just single click it, I only get one image. Let's try with Paint. See what happens with Paint. Open with Paint. So let me move this over. So it's not clear at all that there are 2 images that are part of this. Okay. Normally, most paint programs or display programs are only going to find the first one. So how would you know that there are 2 images that are mashed up? Okay, let's go to WinHex and open that. And that would be combined.png. Okay, so what you would have to do, so we have PNG right here. We know that it starts off with a valid PNG image. So let's go and search for PNG. And notice that it was found 2 times. And that's our clue, and we can actually use data carving techniques to get that second PNG image and save it to its own file. WinHex makes this pretty nice. Just right click and say highlight in editor window. I'll actually see where it starts, PNG. Okay, and that way I can do my data carving as I need to do.